Right. All right, quick reminder, I believe next week is our spring break. Triple check. Where are we? 14th? Yeah, right. So spring break next week. Last discontinuity in our timeline. Any additional questions about trees before we move along into graphs? Right? Okay. So a graph, collection of vertices and edges. And we've already seen trees, and those are a specialized type of graph. So we're moving on to more generalized graphs. Those are, okay. All right, so there's going to be different types. Fun terminology to start off with. Simple graph. All right, set V of vertices. V is greater than or equal to 1. And we'll have a set E of edges. Edges where E is greater than or equal to 0. And so our simplest symbol graph that we can have, which would be basically like a tree with just the root. Try that again. All right, so my set E, E is empty, V equals comma separate list of vertices, and E is null. It's possible to even have multiple vertices and no edges connecting any of them together. And it's 3 vertices or a set of vertices, just comma separate list. And a null set for our edges.
It's not working.
Sorry, what was that?
How to do?
Do you have a question, Yuma?
I couldn't.
I'll take that as a no. That was an accidental unmuting. Okay. All right. All right, another graph, 3 vertices, A, B, and C. A links to B and B links to C. So we're set here. Same as we had previously, 3 vertices. This time we have a set of edges. The way the edges are done is by listing a pair of vertices. So we have the edge AB, and we have the edge BC. In a simple graph, The edge AB is equivalent to the edge BA. It's a bidirectional edge. So the edge goes both ways. Two-way street. When we're listing out the edges or vertices, we'll follow the convention of making the list alphabetical. The edge length, the way we draw it is arbitrary. But just 1 second. Length will come in when we apply weighted edges. We'll add a decoration to the edge that says how far A and B are, if there's a cost or weight or label associated with that edge. But right now, the physical distance in the depiction of the graph is just arbitrary in the depiction. And multiple edges. Okay. We could have different weights. If there were different weights, we just draw the edges differently. But when we get to the in-memory representation, we'd have just multiple places where we could put that data. And in that case, it would be a directed graph. Let's see. So talk about directed graph. Also known as just a digraph. Yeah. I just spilled some soup on my keyboard last week, so some of my keys are not quite fully back to life here. So just a little. Okay. You're gonna have at least one edge this time. So it's going to be very similar to our simple graph, except at least one of the edges is going to be directed. All right, so we'll add some arrowheads on here. And our set of edges is going to look a little bit different. We have A to B and we have C to B. Here, order matters. So A being listed first means A is the source vertex, and B listed second means it's the destination vertex. That's what the arrowhead indicates, going from a vertex to a vertex, and we're here C to B. Right, if I put the arrowhead on the other side, it would look very much the same as our set notation goes, but with our set notation, we do have to have some qualifying information so we do know what type it might be. Right, so in a directed graph, the edge AB and the edge BA are different edges. So if I were to do that same graph again, add an extra arrowhead on the other side. So now we have AB and BA. Right, so there are three edges in this graph. So way that we handle the digraphs is going to be a little bit different. And this can be drawn different ways. Drawing one, where we physically separate the lines. Same graph. And option 2, where you just don't bother with the arrowheads. No arrowheads. Then that means the edge is bidirectional. So this is a directed graph because there exists at least one edge with a specified direction. If we don't see any arrowheads at all in the graph, then there's no reason to qualify that as being a digraph. It'd just be a simple graph. Next up, we have weighted graphs. Here, we're just adding an additional rule set. All right, so we can have labels or costs or weights associated with the edges in the graph. Those values could represent the cost to transition from one vertex to another. Represent distance or just state change, for example. Right, so if we have sorry, it fell down, okay. Our first simple graph example might have a cost of 5 in this place, and a cost of 4 from this other place. Could be hours, could be hundreds of dollars, whatever the number represents. We'll just say flight time. Take flight times, make these numbers look. It's not quite that far away. Now let's go 3 and 3. Take 3 hours to fly from LA to Texas, and then from Texas 3 hours to fly from there to New York, sort of thing. And we might have an edge connecting all the way across. And see if I can get this to work. There we go. All right, our alternative path, take a direct flight. Get there in 5 hours or whatever it is. And so we're just assigning some weights. So we might have a digraph that does the same thing. Where it might cost us more to get there than it does to get back, because we're flying 3 days before New Year's and everyone wants to be in New York for New Year's, but then we're coming back home on a Tuesday. And or we're going against the winds, talking about times here. rotation of the Earth, whatever it might be, but it's not the same value to go back the other way. Sometimes the same both ways, sometimes different. Right? So if we're doing like directions on this from your house to school sort of thing, the mileage, assuming you take the same route both ways, would be the same, but based off the time of day, if we're actually on campus, right, getting to school probably take a lot longer than it would getting home, because 9:30 at night tends to be quite fewer cars on the road at that point. So we might measure those distances in time, and based off of those measurements, we might decide, in fact, that a different way to get to school and an alternate route on the way back. Right, so when you have your weighted graph, all the edges will have a value applied to them, which can then be used for finding optimal paths and things like that, which we'll get to later. We also have multigraphs. Now, typing is not working, so we're tonight. All right. Multigraph will allow there to be more than one edge between a pair of vertices. Right? You don't want to confuse this with a directed graph. Right? We have not had multigraph yet. LA to Texas at 3, and then Texas to LA at 3.5. Those are different edges because they're listed differently, right? So in fact, let me list out what we had before. We had LA, Texas, and New York, and then our edges. We had LA, Texas. Do a dash, it's easier to read. We had LA, New York. We have New York to Texas. Oh, LA, because that one's bidirectional. New York, Texas. And then last we had Texas and Texas, New York. Make sure you get that right. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 edges. Right, none of these are repeated. Unless I goofed up when I was doing here. The other reason why I'm going alphabetical. 2 edges where LA is the source, right? We've come look at our LA node. We have 1 outbound edge there and 1 outbound edge there. New York, 2 outbound edges, 1 there, and same with Texas, an outbound edge and an outbound edge. Right? None of these are repeated. This is not the same as that. That's not the same as this one, et cetera, et cetera. All right, so our multigraph. And let me go back before I had any numbers. Multigraph is just going to allow multiple edges. So there's our multigraph. So it's going to be a simple multigraph because none of the edges have direction. We have our 3 vertices in our set. Now we have AB, AB twice. So they're saying there's 2 ways from your house to school, but we don't have any extra details being stored about that just yet in our data set, but just that there are 2 ways. And there's 2 ways for you to go in your bathroom. Go to your, in the bathroom also works, but not what I was going for. To your bathroom, you can go to the bathroom that's upstairs, you go to the bathroom that's downstairs. Either way, slightly different destinations, not the best analogy, but I guess the first way when I went, okay, multigraph. Just need a repetition of at least one edge in the graph. All right, so that will be a simple multigraph. And simple graphs are the default descriptor we would have to a graph unless it's not just following into. All right, so directed multigraph, same idea. We just have direction. So to make this a multigraph, we have to keep the directions on these arrowheads the same. These are going in opposite directions, that would just be a diagram because we would not be repeating any of the edges in the list. All right, it's the same three vertices. Now we're going to repeat the AB edge, EC, CB. Right, so we have four edges, 1, 2, 3, and 4, since that one goes both ways. And we have repeated. Right, repeated the edges makes it a multigraph. A pseudograph, last type of graph for now. This is just allowing single node loops. And just to point out, there's a little bit of variation in various resources. In the multigraph, pseudograph, some will say multigraph allows some variation. Whenever there's variation, I try to make sure that we're consistent on what we have in our documentation, so we're on the same page. But we have an edge AA here. In addition to our AB, the A, and we got there. BC, all right, so we have, okay, we're done in here. So that's just a simple graph. List them all out. So we got AB, BC, all right. 3 bidirectional edges, one of which is looping back to itself. What is a pseudograph used for? Finite state machines is typically where we would see that being used. Give you an example of that one later. But, in the math class, you'll go over it. Typically, it's vending machine is what we use as an example, where you have your initial state where there's no money in the machine, and you can push the vend button to vend candies, water, soda, whatever machine's vending, and it's going to check the state of the money entered against the price of the object you're attempting to vend. And if you don't have enough money in the system, it's going to put you right back to the same state. You're still at the same state that you're in. So most states on the vending machine have a loop back to itself. So on button press, it loops back to itself and it's still the same amount of money. But if there's actually enough balance in the state for the money entered, it can transition you to a different state or cause actions to happen on transition, such as vending the item, issuing change, right? There might be a cancel button that just gives you your money back and takes you back to our initial state. Sometimes graphs will have particular shapes associated with them. Talk about cycle graphs, star graphs, wheel graphs, complete graphs, bipartite. I always try to hyphenate it. I think it always tries to correct me. Bipartite and complete bipartite. Partite. It's going to be another place where some authors will differentiate on the description. And these are all just simple graphs at the foundation until we get to bipartite. So a cycle graph is just a polygon. Polygons starting at a triangle. Degree of every vertex is going to be 2. So that's new degree is the number connected to a vertex. Stable, how are we coming through? Sound check, thumbs up, plus, minus. No one can hear me.
You're cutting out, Professor.
All right, let me switch to my phone as the hotspot. One moment. So I might cut out more for a second here. Okay. As soon as my phone shows up. Good now. All right, well. All right, keep on rolling then. Okay, so degree of vertex, number of edges connected to a vertex. So when we get our cycle graphs up here, get a few edges. I'll initially draw them so that they actually look like the polygons in question, or at least close to it. Angles might be slightly off. All right, so here we'll have our first cycle graph. That's going to be a C3, 3 representing the number of vertices in the graph. Each vertex has 2 edges that are incident with it. It's as similar in concept to the degree. All right, so it's going to be your C3. Let's see, can I do subscript in here? Yeah, I'll just leave the text outside. Our C3. C4 and C5. No, that was it. What is my format? Comma. Shift, comma. Not working. Oh. Just no shift. That would be why. Right. So each of these has 2 vertices. So whatever this bottom right corner vertex might be labeled 2 edges connecting to it. That makes the degree 2. 2 edges here, 2 edges. And it's just polygons, you know, pentagon, hexagon, septagon, octagon, so on and so forth. Those would be our cycle graphs. They're making one cycle. So you could start. So if we wanted to make a path, on these graphs, we could start from anywhere and walk down edges and end up back where we started. Star graph. It's going to have a central point from which all other points are connected. It takes 4 vertices for it even looks like a star. But we can have as few as one vertex in a star graph. So let's go ahead and draw those out. So there's our first 2 star graphs, an S1 and S2. Kind of funky to call them stars, but they're working their way up more or less. To looking like a star. This one kind of looks like it. Probably best if I redraw this one. We get there. We'd say that's the center point. This one's kind of arbitrary, which one we're saying is the center point. We'll go ahead and color one of them. Yeah, let's go ahead and change my angles here a little bit. Make it look more star-like. This is how we'll more or less grow. Just keep adding. More edges. More vertices connecting to that center point. And this is more or less how the internet grows. The internet is just a collection of stars that link together. There, S1, S2, S3, 4, and so on. This one again was an S4 as well. S5, S6. Right, some authors, for whatever reason, do not want to count the central vert in this count, and that just makes them inconsistent with the other graph shape. Or their cycle graph, this number represents the number of vertices. So what we do is we stay consistent with the other shapes. Really, once we're at a 4 vertex graph, that's when it starts to look like a star. Next up, we have wheel graph. wheel graph is the composition of a cycle and star graph. Basically, take a star graph and wrap a cycle around the perimeter. I forgot to mention some degrees in here. So of every vertex in the star graph is 1 except for the central point. Degree is the number of vertices minus 1. There's a V pipe. This equals number of vertices. In the right, so S1, one vertex in the graph. The degree of this one vertex is 0. It has no edges incident with it. And our S2, which can be our slight anomaly because all the vertices in this graph do have a degree of 1. So we have our external vertex that connects to the center of 1, and then we just have one internal vertex or perimeter vertex connect to the center. So this one also happens to be 1, but still it's 1 less than the number of vertices. S3, 1's again on the perimeter, and then a 2 in the middle. S4 is a 3 in the middle. S4 again, 3 in the middle, and the right number is less. Whatever this value is, the degree of the vertex in the center is 1 less than that because everyone else connects to them. All right, so the degree of the perimeter vertices will be 3, and the central vertex, just like it was with the star, is the number of vertices minus 1. So I can take yeah, forget that one. Let's go here. Take my S3, excuse me, my S4, wrap 3 edges around the perimeter, and make it a wheel. All right, wheel looks like a bicycle wheel, or at least approaches looking like a bicycle wheel once there's a sufficient number of spokes in the star, and then we have our tire on the outside. And make that a little bit. Okay. All right, so we got our W4, still the same number of vertices. W5 and W6. Okay. Any questions at the moment? That wheel's looking pretty terrible. Let's straighten that up. Okay. Complete graph. I mean, this graph connects as many vertices to each other as possible. The degree of every vertex in the graph is the number of vertices minus 1. So here we can somewhat trivially start at a K1. And we're using K because C is already taken. So we have our K1 graph. It is as fully connected as it possibly could be. A K2 will just be two vertices talking to each other. K3 and a C3 look the same. Degree of everyone will be 2 because there are 3 vertices. K4, everyone's going to have a degree of 3. And the way we draw these is somewhat arbitrary. There's lots of different ways to star graph that we might draw particular shaped or any graph for that matter. What matters is the set of vertices and the set of edges that are in the representation. All right, so there's a K4 to a K5. All right, so we're adding one vertex and connect that vertex to all the existing vertices. Yeah. Try again. Connects there, connects there. See if I can get that curved, curve a little bit better. All right, there it goes. Oh, it's always fun when the code doesn't want to work with you. Whatever, it's connected. Every vertex has 4 other vertices connecting into it. So got our K1, that was interesting. Cursor is one place, types another. K2, K3, K4, and K5. Any questions about any of these shapes at the moment? Bipartite graph. This graph is to be separated into 2 sets. Can name them whatever we want. We'll just go with set A and B. Rules for this graph is that there cannot exist an edge within or between a pair of vertices that all right, so let's look at a graph and see if it is bipartite or not. All right. Set A and set B. All right, so we'll grab a vertex and we see that it is connected to 2 other vertices. So neither B or C is allowed to coexist in set. In fact, let me change the labeling here. Let's call this PQRST. PQRS. All right. Vertex P connects to both Q and R. So P cannot be in the same set as Q and R. So we move along to Q. Say Q is connected to P and S. Saying can't have S in the same set. And we come over here and make sure that our connections are good. So we've separated in our two sets, and we could just redraw this differently as our two sets. Right, so we have P and S both in here. So we just grab P, grab it. P and S and Q and R. Right, so this particular cycle graph is also a tight graph. Right, there's no edges between the vertices within set. And either set can have an arbitrary number of vertices in it. All that matters is don't have any edges defined within the vertices within the side of the same set. Right, we'll typically use this graph for matching jobs where we want to do various tasks. And have various people available to complete those tasks. All right, so one set could be people, and the other set could be various jobs. So we've got Bob available for work. Tina, Alice. So on and so forth for whoever it is we have. Roommates, employees, whatever. There's work to be done. We need to figure out who's going to be doing. Just retype the same name twice. Alice and Alex. Okay. All right, so let's say someone's going to do the design document. Someone's going to do the UI. Someone's going to be doing the SQL. And then someone's going to do the application behind all that, what are various tools. So the reason we have this set up as a bipartite, because it makes no sense for there to be edges between different people inside this set, or there to be edges between this set, because the design is not going to make the sequel exist, and the app's not going to make the sequel exist. This means not using any tools that I can actually, some of the tools can, of course, generate your DAO from the sequel and vice versa. But still, there's still all the application logic that needs to be done. Bob is the designer, so he's well suited for doing the design. And he's got a little UI experience, but he does not know it. He couldn't tell you a table from a view or any of the other fun stuff in SQL, so he's not going to be able to help there. Tina is a developer and writes code in whatever language you put in front of her, so it's good to help out there, whatever. And Alex is just SQL. So the edges purely exist across the sets, not within. And that's how we'll start laying things out. The next step would be to actually start putting times on these, or story points, weights, sprints, whatever. We want to represent how long it's going to take things to get done. And it's entirely possible one person in here could actually do everything, because there's that experience. Problem is their experience is light in all the areas, so we can't rely on the one person to do everything, because it would take 2 years to get the job done. And we have all these other resources available to help expedite that. So that's how the data will be represented. You can also do a composition with a complete bipartite. Right here, we're taking the two rule sets and mashing them together such that cannot have edges within a set. So between the two sets, there are as many edges as are possible. There's a thing to note there. Degree of every vertex in set A is equal to number of vertices in set B, and vice versa. And we will call these KAB for our notation. A being set A and B being set B. So go ahead and make one of those. And then just skip the background. We'll put it in there. May as well. Okay, so we have 4 vertices in the first set, 2 vertices in the second set. All right, so that means we'll have 2 edges coming out of every vertex in this graph on the left side, and then 4 coming in to All right, so we're going to do our 1, 2 from each vertex in the left set, and having done so causes there to be 4 attachments to every vertex in the right set. So we get a lovely spider web going on here, and the spider web would be a real world example of a graph type representation of data, right? Get the strands and where the strands connect. Those intersections are the vertices. Same thing for a map, right? Thomas Guide or Google Maps, whatever. Intersections are vertices, and then the streets are the edges in between those vertices. Other places we'll often see graphs. Right, a computer is a vertex, and the connections between that computer and other computers or other devices, routers, for example, those connections, which might be wireless, same difference, or wired, are the edges, and the machines themselves are the vertices. Right, so if we go ahead and I was talking about earlier, go to the internet. Right, this image has been around for a long time, but that's so annoying. Try to zoom in on the picture. And it just wants to not work with us. All right, so at some point in time, someone wrote a crawler and they had to crawl the internet. Basically, there's going to be some central points here, major connections between DNS servers and the other main servers that form the backbone of the internet itself. Then you'll get out to, like, maybe this is UCI or this is IVC or something like that. Get into IVC, then there's just a ton of machines connected in that network, and this could be several stars on top of each other because they have several possible entry points into that network. So it's just a star of stars effectively is what more or less the internet is. But then there is going to be some duplication, these lines that go across. We can find some cycles in here, but the primary composition is a bunch of stars layered around. The sphere that is the internet. Okay, let's get back to normal zoom. All right. But while we're here, cycle graph. So you see on the right hand side, it's bigger. We'll have the numbers over here showing these fun things plus other additional things that you just need to read up on for the chromatic fun stuff. Right, notation, CNN. Have the other links on here? No. Okay. Star graph, right? So location is still S of K. You can see, note we have the two things here. We are going with, there's 1, 2, 3, 4, 5, 6, 7, 8 vertices in the graph, then that is the number. It's on Wikipedia. They have K plus 1, and that just makes us inconsistent with the other types of the word. Don't like inconsistency. Consistency is better. Real graph, right? Which a star graph is very similar to. And you can see their W4, 4 vertices. So why is the star graph different? Could be who came up with star graph first with the other notation. Other people came up with the other types, and they had different notations, and they never unified it. Who knows? All the fun properties and the details. Wikipedia. Oh, grab those links, toss them in here. Yes. Any questions about our various shapes that we might have? A graph B. Okay, consistent. And we need our complete graph, enter bipartite graphs. Second. I already put everyone to sleep, so you got no questions. Keeps it easy. Okay. Yes, I did mean what I couldn't type. Right, see here they're using the notation of N and M. I've also seen U and V. Right, the labeling of the sets is arbitrary. Just do A, B, not that there's really a preference for one versus the other. All right. So we've been drawing the graphs on the screen. The computer is not going to be working with an image. All right, so we need to get into our data structure, which is going to be our in-memory representation. There are multiple ways, several ways to represent graph data in memory. We'll cover the adjacency matrix and the adjacency list. And there are other ways, but these are the two that we'll get to. Right, so the matrix. This is going to be a square array where the size of the array is the number of vertices by the number of vertices. Label horizontal and vertical axes with the labels of the vertices. Right, so for a simple graph, we use binary matrix. If an edge exists between a pair of vertices, then we'll set corresponding cells, two cells, to true, right? Because the simple graph A, B, and B are the same. If an edge exists, both of those positions will be set to true. So let's do an example of that. I click where I want to click. All right. Okay, so A, B, C, D arbitrarily named vertices, and we'll toss in a few edges in here between the pairs, right? So it's a simple graph because there's no directionality. So we have 4 vertices, so I'm going to need a 4x4 matrix. Plus, I need my labels. So when we're doing the labeling, out of consistency and for our convention for the class, the labels are in alphabetical order so that if I were to give a picture, there's exactly one matrix that could possibly exist for it. And it would be the same across the board. So A does not connect back to itself. So we put a 0 there. So from A to A, we have a 0. From A to B, we do have an edge, so set a 1. From A to C, we have an edge, so we'll set a 1. And from A to D, we have an edge, so we set 1. A has 3 edges incident with it, and we have 3 cells turned on. Move down to B, same idea. Does B go to A? Yes, it does. Does B go back to itself? It does not. Does B go to C? B goes to C. B does not go to D. So we'll set that off. 2 entries on, degree of 2 for B. C has a degree of 3. All right, so it connects to everyone except for itself, just like A did. D has a degree of 2 connecting to A and C. A and C, B and D, no edges. All right, so the list, the adjacency list, same idea, much like we've had in other places. We have array-based or we have link-based options. So the list, this is going to be an array of linked lists, singly linked, typically, where each list represents those vertices that are connected to a source vertex. Let's see, we'll do this 2 ways. No, that's not doors. Okay, so let me grab a screenshot. So we have 2 going at the same time. All right, so for the same graph, what we're going to do is have an array right? A, B, C, and D. Those are our vertices. Then what we'll do is for those edges that, for those vertices that have an edge between them and the source vertex, right? So A goes to B, A goes to C, and A goes to D. So I'm gonna have 3 entries over here in the A list. A will go to B, C, and D, E, C, and D. And we'll do the same thing for everyone else, right? This goes both ways. So B goes back to A and goes over to C. So we'll have 2 in this particular list. B goes to A, and B goes to C. Keep on going. C goes to everyone. So it's very much like this list. Just go ahead and change our letters out a little bit. You can see connects to A, B, and D. And then D goes to A and C, much like D did. All right, D also goes to A and C. All right, so let me bring focus here. So One of the things that a lot of people like to get tripped up on. This particular here, a link from B to D. There is not an edge in this graph from B to D. And that's not what this means. These edges are just a list of values. This list of values is associated with the source vertex. C goes to A, C goes to B, C goes to D. B does not go to D, right? So make sure when you're looking at the list, you're not getting those two details confused, because that is an area that people like to fall down on. Okay. All right, so this time, digraph with matrix and a list representation. All right, so the more vertices that we have, the bigger the matrix is going to get. Let's name them A, B, C, D, and E. And that's for a digraph. Not all of our edges have to be directed. So we'll just do a few in here. That's good enough. So our matrix, we have 5 vertices. We need a 5 by 5, which we'll do in here as a 6 by 6. So we have space for our labels. Again, labeling alphabetically. All right, so like before, A has all of one outbound edge. That's going to be, everything else is going to be 0. So when we're reading the matrix, it's source to destination, where source is the left side and the destination is the top, over here on the right, or above rather. B has 2 outbound edges, one going to A, one going to C, and everyone else is 0. C has 1 outbound edge to D, set everyone else to 0. D has 1 outbound edge to B, set everyone else to 0. And then E has 1 outbound edge to D, and everyone else is 0. All right, so it's not a very or heavily connected graph. So we go ahead and draw our list. Let me steal this one. And on top of it, all right, E just has the 1. A has just the 1. Goes to B. B had the 2 going to A and C again, still so that one happened to be the same. C just goes to D. So I can lose these last points. I copy paste. D was just going to B. And E was just going to D. And oh, that was interesting. All right, E goes to D. And let's type D. Let's type and say the same things. That's always good. All right, so let's double check our work. We have 1, 2, 3, 4, 5, 6 edges. 1, 2, 3, 4, 5, 6 entries in our lists. right, so we have the right number of edges at least. Question is, how come we use a matrix before this? So we would use one or the other when we're presenting the graph. We wouldn't have both representations at the same time, most likely. Typically, you're going to have one or the other. And next question, why can't we build the graph just from a list like a tree? The tree by list, right? Like, talking about array based, where we have an array representing a tree, we can do that if we know the areaness of the tree and do a growth pattern here. The one we're going to choose is going to be driven based off of how connected the graph is. So this particular graph is lightly connected. The number of edges relative to the number of vertices is quite low, right? 6 edges against 5 vertices. So in that type of situation, we'll probably be using the adjacency list because these lists are so short. Get a little bit of better space utilization. So that's the drawback we have with the matrix. Every time we add another vertex, so I wanted to add another vertex to this graph like I did before I went from a 4x4 to a 5x5, I go to a 6 vertex graph, now it's a 6x6. Now we're going to get 36 elements. We have quadratic growth for how big the matrix is relative to the number of vertices. So the space complexity can be a little bit hefty there. And if it's for a graph like this, where most of it is 0 state, we're a little bit wasteful in our memory allocations there. Did it answer the question? Not sure fully. All right, cool. Yeah, so matrix and the list, those are just the 2 ways we can represent at least the 2 ways that we're covering will represent the graph. All right, let's go ahead and let's take a 5-minute break, and then we'll keep on looking at the other graphs and how they get represented over here. So go ahead and mute. See you in 5 minutes. Okay. Let's go ahead and do a C5. And it doesn't matter how things are drawn. Well, this, as we see the representation of the graph, has become a little more obvious. So here we have a C5 matrix. It'll be a 5 by 5. The degree of everyone's going to be 2. All right, so A goes to B and E, B goes to A and C, C goes to B and D, D goes to C and E, and E goes to A and D. All right, so if I don't put an entry in there, that's the same thing as no entry or 0, null, however we want to look at it. Every single row has exactly 2 entries. And since I happened to do my vertices in alphabetic order, there's a little bit of a pattern. This pattern is not necessarily present. Depends on the labeling of the vertices. But the pattern that will be true is there's going to be 2 entries on, because that's a cycle graph. A cycle graph has degree of 2 for every vertex. All right, corresponding list. Same thing, 2 entries for every vertex. Just a matter of lining up values. A went to B and E, B went to C, C went to D, B and D, D went to C and E, and E goes to A and D. All right, so since they are shaped graphs, oops, going to tend to have a particular pattern in the representations. All right, wheel graph. Same idea. Right, we have everyone with a degree of 3, except for 1 point. So let's go ahead and get our wheel here. All right, so we got our cycle around the outside, and then everyone connecting in to the center point. All right, so we're going to have a degree of 3 for everyone on the perimeter. Then we have 1, 2, 3, 4, 5 for C, who happens to be the one in the middle. 6 points. All need is 6 by 6. Right, 3. So everyone connects to C. So we can go ahead and set that column because C is the central point, and then same difference here. C connects to everyone else. Just leaving 1 off point for C to C. Then we have our neighbors on the cycle part. So A has B and F, B and F. B has A and D. A and D we already did C, so we'll go ahead and go to D, who has B and E. It's breaking and entering. That's just terrible. What a rude node. E has D and F. D, F, and then F has A, D, A and E. All right, so 3 for every row with the exception of our central point, which is going to have everything turned on. And double check your work. Our columns also have 3 for every column, with the exception of our central point. Let's see, I think we did complete graph next, right? Let's see. So, same order, complete. All right. Here we're going to be as connected as we can manage. So I'm going to skip the drawing because it's just everyone connecting to everyone. And we'll go straight to the structures. So if we have a 5 by 5, with whatever we're labeling things to be, we're going to have a 0 on the diagonal because it's still a simple graph. We're doing a simple graph. Simple graph, we do not connect to ourselves. And then the degree of everyone will be 4 because there are 5 vertices. So every other data point or every other element in the graph is going to be turned on. So the corresponding matrix, which I guess I skipped for the wheel graph, let's get that over there as well. Swing back matrix. I even said the wrong word. So we have our adjacency list. So going back to our wheel graph, let's draw it. To the side, it's good. Okay. All right, so C is going to be our long list, connecting to everyone else. So we'll need 5 entries there. So we'll have everyone listed out except for ourselves. And then we're going to have 3 across the board elsewhere. All right, so A is going to have C in its entry like everyone else, but we also have B and F, and we need to do it again in order. So we have B, C, F. B has A, C, D, A, C, D. And we've already done C, so that's good. Move along to D, B, C, E. And then E, we had C, D, F, C, D, and F, and F is last with ace. All right, let's get a little small. And our complete graph is going to look quite uniform, just like the matrix did. Just have our various entries. There's going to be 4 in each list. So the list is going to look quite rectangular in nature. And that's just because it happens to be a shaped tree. We just have a general tree, it's just an arbitrary set of collection of vertices and edges. Then it's just going to be whatever. So this is A, so we'll list out every but A, B. I'm short one, aren't I? Okay. Nope. let's see. So we're going, this one we're doing backwards, right? So we don't actually have the drawings. We have 5. Okay. All right. So basically, I say do a K5 with the vertices A, B, C, D, and E. It's going to look the same. So it connects everyone but itself. Everyone but itself. If I don't type itself. A, B, D, E, C, E, and then A, B, C, and D. Right, and this time we're going to go the other way. All right, we're going to go ahead and draw from the adjacency list. And so if we have this particular adjacency list, we want to go ahead and try to draw it. So we come along and start drawing. Basically just go through the list. Okay, we have vertex A. And we see vertex A connects to vertex B. All right, so go ahead and draw it in there. And we see, okay, A connects to C as well. So we'll add it along in the graph somewhere. Attach it, say, okay, it connects to D. And it connects to E. All right, so we process basically this row in the list. We just go to B, BA, all right, that edge is already there. B goes to C. Okay, so we just need an edge between B and C. B goes to D, another edge in the graph, and B goes to E. So we just keep on adding edges. B goes to E. Rinse, repeat. C goes to A. We've already got that. C goes to B. We've already got that. You add in D and E. C goes to D and C goes to E. Keep on going. Just draw what we got. DA is in there. DB is in there. DC is in there. Need. Then lastly, DE. All right, and it is connected. All right, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4 edges coming out of every single vertex. And that is a K5 graph. And there's more than one way we can draw this. And I just draw them out as a flat line. And then connected it up. Let's fix my labels here, A, B, C, D, and E. All right, A connected to B. And it connects to C. And I'll get to that in a second. Just get my line through since we know that's going to be there. All right, curve connectors, let's see how we do. A goes to C. A goes to D. A goes to E. A is there, B, C, B, D, B, E. All right, connect up C, back to B and A is already done. To D, now I jump over here to E. And D, all right, connected next up there. It's connected back to C, back to B, back to A. And there is our K5, right? Same graph, just laid out differently, right? Everyone with me there? These are the same graph. The way that we draw the graph is immaterial. going to skip along to the complete bipartite, because that definitely has a pattern in the data. And this one will also go ahead and just do the matrix first and move along from there. So A, B, C, D, E, C, D, E. All right. All right, so this is going to be our complete bipartite. Just take the math class, you'll see that this graph can be simplified by not listing everyone on both sides. But let me make sure I did this right. Let's see. I think I went too far. I went too far. This should be over there. There we go. All right. All right, let's see if I did my matrix right. We'll go ahead and draw it and then go to the list. All right, we've got A. A connects to C, connects to D, and connects to E. C, D, and E. And we have B, also connects. B connects to C, D, and E. C, D, and E, and then come over to C, goes back to AB, D goes back to AB, and E goes back to AB. Right, and so what we have is our two sets. Send to the back. And send that to the back. And thus we have our bipartite, and it's complete. As opposed to just a regular bipartite, because we have full connectivity, right? Degree of every vertex in set A is equal to the number of vertices in set B, and the converse is true. Degree of everyone in set B is 2, because there are 2 vertices in set A. And list. And we'll also have patterns here. Right, based off of connected pattern, right? We're going to have 3 entries for each of those in the first set, and 2 entries for each of those in the second set. Okay, so A, C, D, and E, and B has the same set, and then AB, AB, AB for everyone that's in the second set. All right, so that's all with just simple graphs, right? We're just doing binary relation, all the various shapes that we have there. How are we doing at the moment? All right. More in the data structures. This one we're going to do a digraph. All right, so with our symbol graphs, we had mirroring going on there. Let me make sure. Right, just like it's easiest to see with the complete graph, the mirroring, right? We have the diagonal, and everything mirrors across that diagonal. Everything on these values, they line up, right? The ones lining up across that diagonal. Right, so you have a plane of reflection going across that, a little funky looking antenna. And that is true for all of our symbol graphs. If we look here, we'll see the same thing. There's a mirroring going across that diagonal. And that's going to be true for all these graphs because all these graphs were symbol graphs in nature. So go ahead and move on to a digraph. Digraph presentation will be the same as we had the symbol graphs, but we're not likely to have the mirror plane across the diagonal. Diagonal. Okay, do both ways. First one we'll go ahead and do with our drawing and then go from the reverse and go from the matrix or the list. And then back. Just do some arrow connectors. This one can go both ways. All right, 5 vertices. So if we're going to do the matrix, right, so A has one outbound to B, B has one outbound to C, C has one outbound to D, D has 2 outbounds to C and E, and E has no outbounds, so that row will be empty. 1, 2, 3, 4, 5 edges, 1, 2, 3, 4, 5 ons inside the matrix. So we draw this as a list instead. Let me go steal. All right, D does have those 2 entries, but everyone else just happens to have the 1. Let's see, I saw a comment. Let's see what that says. You try to implement a data structure system for a project. Is there a standard procedure to follow for what the data is going to be used for? Well, each case wouldn't be unique, but it just depends on what you're doing. Right, so what the application needs to do is going to drive what data structure or structures would be appropriate. When we get to the last data structure in the course, hash tables, aka dictionaries or hash maps, we'll see that that one's used quite a bit. Right, regular arrays are going to be the most commonly used data structure, and we don't have necessarily additional structure around the arrays other than possibly being sorted, in which case we get binary search out of it. And often we'll use vector or other library implemented versions of those arrays because that handles the resizing for us. We don't have to go in and code that because resizing an array, and that's often typically a need. So if an array needs to be non-fixed size, typically we'll use a vector in C++ and equivalents in other languages. Like .NET calls it just a list, in which case it's an array, not linked list. They actually have implemented linked lists separately, but it all depends on what you're doing. Most of the time, an array is going to serve your purpose, or multiple arrays will serve your purpose. And when we get to hashing, hashing is built on top of arrays. It's just adding an algorithm on top of the structure for how to get to the data, as opposed to actually really changing the structure itself. Graph data, the appropriate representation, that is going to be driven based off the data. If it's fully connected, probably going to go to the matrix. So again, now we're talking about array versus lists, right? Arrays have advantages, arrays have disadvantages. Lists have advantages, they have disadvantages, right? So it's easy to resize the list, not easy to resize the array. So if we have a map and we keep discovering new places and want to add them to the map and add the roads that are connecting to this new place that we found to the places that we already know, that that means resizing the matrix probably means rebuilding the matrix, which means slightly expensive operation. So yes, what the nature of the data is a key factor, and then what we're doing with the data is secondary factor, and then for the what are we doing most often? Because it might be very expensive to build or rebuild the matrix or list, but once we have it, are we using it often? And what's the use? Are we keep adding and removing edges because we're maintaining a table like in a router? So routers maintain, what are those tables called? I just forgot space on what those tables are called, but a router is going to connect to various endpoints, and our router's job is to route packets from the source IP to the destination IP, and that IP has to be figured out to where we're going. And it's very rare that, like when I go search to Google and I find some random website, that my computer is going to have a direct connection to the host server for that website. I'm going to be routed through my local ISP. That ISP is going to then get into the backbone, and the backbone is going to go over to the ISP for wherever that provider is, over in New York or Florida or Arizona, wherever they happen to be, and then go through that ISP's network, and then ultimately get to their data center. Assuming there's a data center, it could be just someone's computer sitting underneath their desk, right? And they might have 2 or 3 routers and switches and or firewalls that the packets are routing through just within their system. Right, so the routing tables, I think that's what they're called. Right, they got to maintain this information for where they can get to, how long it takes to get there. Right, what's the ping between these? Because traffic is flowing across the internet all the time, and sometimes you get bottlenecks, and not all the packets are necessarily going to follow the same route for a given bit of communication from point A to point B. So those tables are perpetually being updated, and packets are just going however they go as long as they get there is the key thing. For like just uploading or downloading a file, we don't necessarily care about the order too much because that can be reconstructed on the end. But yeah, as with pretty much everything, at least 70 to 90% of the stuff we talk about in the class is all is going to boil down to what do we know about the data, if anything, and then what are we going to do with the data? The what we should know, because that's the whole purpose of the application. The application is going to do the what's, but the data that it might be dealing with could be from external sources and various external sources, and it might be very very different, a lot of variation in that data. So we just have to do the best we can. And we find reality is like, whoa, we've got 2 or 3 different patterns going on here. So we got to try to figure out what the patterns are and then find data structures that'll better suit the need. And there's several times at the company I'm at presently where we found bottlenecks in the system, taking a memory dump, find out what the bottleneck is. You know, it looked like a memory leak because it's like eating up all the RAM. It was just a bottleneck. Things were just slow in a particular area. And actually, whenever this last semester, you know, it was just building an array, and every time you wanted to add a value in there, I had to do a duplicate check. But since we didn't have any structure around it, it had to do a linear search. And as the numbers got to the thousands, the tens of thousands, I forget how big they got, maybe hundreds of thousands. For the lists that I was building, checking to see if there ever was one in there, the linear search was quite horrible. The application was always busy and logging nearly nothing because it was so busy trying to do the one operation. It basically never, ever got its job done because we get a new data set every day. And it was literally taking more than a day to batch process that data. So we had to look and see, okay, we changed the algorithm a little bit. I think I changed it to a hash table. And it would have been better if I just did a binary search after all, the overhead. Anyways, we'll swing back to that later. So our list here, A goes to B, so we're in there, B goes to C, C goes to D, D is going to C and E. I'm not trying to move you. C and E, and then E goes nowhere, so this list will be empty. Right, 1, 2, 3, 4, 5 edges, 1, 2, 3, 4, 5 entries in our lists. Yeah, thank you for the questions. Questions are always good. Let's see what's going about here. All right. All right, so this digraph that we happen to have here is quite sparse. The space that we're taking in the matrix, we're wasting space, but because it's just, there's no weight or no extra complexity. It's not a multigraph, it's just a simple digraph. This can be represented very smallly still. Right? We basically have an array of 5 bytes. And each byte having 8 bits means we have no problem representing 5 possible values. So literally we can have 40 bytes of memory representing this data, or it could be an array of bools. Things get a little bit sticky when you try to do just true binary in high level languages. They don't tend to mesh very well, but we could very easily do this in 40 bytes to represent this entire set of data of this array. If it's a linked list, right, each pointer is 4 bytes, so we're going to blow away the memory requirements very quickly. The link-based approach, the array, we have random access. Right? If I want to know if A goes to B and I know B's position, I just jump to there in the array and say, is that 0 or is it 1? Yes or no, and then I know they're neighbors or I know they're not neighbors. But that's the idea. So we won't do any of our shape graphs in this one because there are no shaped digraphs. I suppose we try to do a star graph where the star just went out from the center point instead of coming back in, but that probably could be a shape. In fact, there are way more shapes. There's probably 30 or 40 different shaped graphs out there. Is it Wolfram? I think. And they have, let's do star graph. Interesting. What? Oh, it's still loading. Okay. I guess my internet's moving. So, anyways, graph shapes. Let's see. I'll have to find a link for you later. There's all kinds of other graph shapes out there as well. It's just a rule set and it's that particular shape, and it might have their application, or it might just be a mathematical construct effectively. Okay. Now, when we move beyond our two basic types of graphs, simple graphs and digraphs, a binary matrix and just a basic linked list is going to fall short of what we need. All right, 42A, 42B. Forgetting the order in which we did things. Let me go check. Simple, would you weighted? Okay, weighted. Weighted graphs. All right, so beyond just the existence of an edge between a pair of vertices, also need to account for the weight of that edge. So instead of a Boolean, we'll need an integral type or a numeric type. Guess we need floating point as the element data type in the matrix. And we'll need to add a field to the node type for the list. And we'll just keep these smaller. 4 nodes should be plenty. And add some weight. So 2.4. We'll go floating point. May as well. 2.4, whatever between these two places. 4.9. And 2.0. And we'll just label them A, B, C, D because the labels are arbitrary. Let's see what the data structure is going to be. All right, so for our matrix, 4 vertices, we'll still need a 4x4. A goes to B, 2.4. It is a simple weighted graph, so we are mirrored again. B goes to C, 4.9, mirrored. And C goes to D for 2, and we're mirrored. Right, simple. So we have 3 edges and 6 entries. And we go steal. All right, so have it like before, grab the image. Much like we had before, but when I had additional data, right? So A goes to B, and it costs 2.4. It's gonna work. Need more space. All right. Okay, with A, B, C, and D. A goes to B, and it costs 2.4 to get there. B goes to C, and it costs 4.9 to get there. And same idea for the rest. And B, C, D, A goes to B. E goes to C and A. So I've got my data point there. Let's get that in there. A at 2.4. All right. C goes to B and D. And then D with our single entry. All right. C goes to B for 4.9 and to D for 2. And D goes to C for 2. All right. So the nodes need to expand. And the cost to go to those corresponding nodes. So from B to get to A costs 2.4. From B to get to C costs us 4.9. So depending on which way we want to transit, the corresponding cost and where we're going to, all within that node. All right, so still representing the same data in both representations. It's just underlying data structures on how we're getting there to do what we're doing. And symbol graph versus digraph, or if we put edges on here, it's just going to reduce the connectivity. All right, put an arrowhead on a couple of these, and that just means we're getting rid of some links effectively. All right, arrowhead. Take this, so we got rid of our AB, and we got rid of our DC. So let's go ahead and knock those off. All right, 4 edges. One from B to A, one from B to C, one from C to B, and one from C to D. 4 edges, 4 entries. If we continue, and make sure I got my lettering right here. Maybe, okay, I did, all right. Or 0.2C, a weighted multigraph. That's the number of data points that we're doing now is getting significantly more. And I'm going to keep my vertices down here. All right, so we have both multiple edges, or actually, let me get ahead of myself here. Getting ahead of myself, multigraph. just multigraph. And if we do the matrix, 3 by 3, ABC, ABC. Here we're going to be doing the counts. There exists 2 edges between A and B, and it's a simple multigraph, so we just mirror it. B and C has 1. Right, so 3 edges, 3 total count. Doubled because it's simple. So we have 1 plus 2 is 3, and then the mirror 1 plus 2 is 3. 4 edges. Let's just do multigraphs. Let's do them all here. So let's do the same thing and add direction. Have them both go to the left. All right, so I just got rid of 2 edges. From this graph, A no longer goes to B. All right, so that's blank entry or 0. We have 1, 2, 3 edges. So B goes to A for 2. 4 edges, sorry. 1, 2, 3, 4 edges. So B goes A for 2, B goes to C for 1, C goes to B for 1. So 1, 2, 3, 4. 1 plus 2 plus 3 plus 4. So we have 4 edges. 4 edges in the graph and a total or a sum of 4 in the matrix. Sitting over here, we have 3 bidirectional edges. And a sum of 6 in the matrix. Right, because 3 times 2 gives us 6 since they are bidirectional. All right, so if we go back to our simple and then get to our weight. So I try to jump to earlier. Have that one be a 1. That one be a 2, and this one can be a 3. Just so we have some nice distinct values. Let's see, can I just see that works? All right, so A to B for 1, A to B for 1, and A to B for 2, and 2. And that is mirrored. So 1 and 2, and then B to C for 3, B, C for 3, mirrored. All right, so excuse me. So we have 3 edges in the graph. So we have 3 entries, 1, 2, and 3 here. Since it's simple multigraph, a simple multi-weighted graph, right? So let me simple multi-weighted graph. Simple meaning the edges are bidirectional. Multi means we allow multiple edges between a pair of vertices, and weighted meaning we have weights on the edges. So we're just compositing the rule sets for this particular graph. 3 edges, 3 entries, because it's multi. Some of those multiple entries are within, right? I can't multi-select, but 1, 2, and 3 are for 1, 2, and 3. And because it's simple, we have that mirroring. So if we go ahead and change this to I'm just going to change the order around, a weighted multi-digraph, because the order does not matter. Just need to add a single arrow in here, arrowhead in here somewhere. And now it's a digraph. All right. Let me add another arrowhead because that one's kind of hard to see. That's a little bit better. All right, so B no longer goes back to A for 2. So that entry is going away. And C no longer goes to B for 3. It has no outbound edges, so empty row. inside the matrix. A multigraph. Let's get the type of fix. Multigraph. Pretty much covers that. Last up we have now is our pseudograph, and our pseudograph is just gonna be the first player to put things on our diagonal. A to A will have values. So times, okay, take a break after we do this one. Pseudograph. Three vertices, plenty good enough. A, B, C, toss some edges in here. And select a couple of them back to themselves. All right, so no weights, no multigraphing, none of other stuff, just simplest form of a pseudograph where we have single node loops. A, B, C, again, alphabetical order. A does have a path from itself to itself, in addition to B. Does not know how to get to C directly. B can get to A, but not itself. And it can get to C. C does not know how to get to A, but it does know how to go to B and itself, right? So it's simple graph version of a pseudograph. Edges are all bidirectional. When all edges are bidirectional, we have, again, that mirror plane. Right, it doesn't really matter if there are arrowheads on the self node, single node loops. That's not changing anything because that's just the one entry. Right, if I put arrowheads on here, one way or the other, that doesn't change anything. That's still the same graph. A goes to A, right? It doesn't matter. It is the source and destination. So the arrow being drawn counterclockwise versus the arrow being drawn clockwise is completely arbitrary. Same graph. Arrowheads, optional effectively. Matrix and list are the same. Right now, the more likely situation you're going to have with a pseudograph is there's going to be weight. Weights. And most of the time, everything's going to be directed. And everything directed. So we'll say we have, let's do the finite state machine. S0, S1, S2. Okay. And might as well put arrowheads on everyone, and there should be one. That takes us back to the beginning. Right, so we have a very limited vending machine. And so state 0, this represents $0 in the system, and we take dollar bills. End of story. State 1 is $1, and state 2 is $2, and everything in the vending machine is $2. So there's going to be a transition that'll get us to move between states. Basically, $1 is entered. and then another dollar is entered. Right? It should be two separate actions because we're not taking $2 bills in this machine. That's too complicated. These actions would be the then button because we have exactly one product. Right? It's a bottled water machine. Everything is a Dasani, all the same size. It's $2. Right? So a very simple machine. Does not have to do a whole lot of thinking. Right? If you try to get your Dasani when you have $0 in the machine, it's be like, no, you're still exactly where you are, and probably emit a message saying $2 or insert dollar bills or whatever. We insert a dollar bill and we press the then button again. It's like, no. Read the sign. It's $2. Right? Some user-friendly message or some message that tells the user that they need to go back to kindergarten and learn math. 1 + 1 is 2, and you need $2 to get there. We'll get rid of that loop. How much needed for this machine? And then that last transition is the then button. Again, they push the then button, but this time we actually cause something to happen. Then, and then we output some H2O. Got to have your dihydrogen monoxide. It's very important molecule. And that takes us back to state 0. And of course, if we're writing an application for this money entered, that's just a variable, right? The different states that variable can have is what the finite machine, state machine is representing. And we now have our weights, so we can go ahead and model that data, our matrix. Okay, 3 vertices. S0 through S1 and S2. 0, S1 and S2. Right, so we do have an action here, and we're labeled it as then. We have an action here, labeling as then. There is no action for S2 to S2. All right, and S2 go to S1 when we do $1. S0 cannot go directly to S2 because we do not have an option for entering into our bill. If we had an option for entering other bills, right, that could then take us forward. So we'd have multiple outbound edges from S0. Right, from S1 to S0, we do not go that way. Right, S1, as we have with this edge here, S2, that's a $1 transition. S2, then with our output, and we do not allow going back to state 1. There's no, give me my $1 back. I want that particular $1 back. All right, there should also be an additional, if it's a nice vending machine, I run into some vending machines that are not so nice, especially the ones that want multiple dollar bills. It's like, it'll give you back that second one. Then that first one, that's been locked away. Thank you for that donation. Right, an extra transition from S2 to S0, it says, cancel. Right, give me my $2 back. If it's the coin-based ones, we're taking dollar coins, that's easier for the machine to handle, but the paper ones, not as forgiving with you being unhappy that the machine is out of the product that you wanted and you don't want any of the other products. But it's still the same thing. We just need the data and the elements somewhere. And whether it's matrix or lists, it's 6 of one, half a dozen the other for a lot of the scenarios. Just depends on what sort of operations we're going to do. Most of the time we'll be doing matrices, because they made multiple matrices, so we might as well use matrices, right? Because we'll often be going we'll build building paths. Path building is going to be a common operation. So let's go ahead and take another 5. Take 5 again. And then we'll continue on. Okay. Ooh, it doesn't work. All right, this code is C#. Make sure you're paying attention because really there's nothing new code-wise that we're talking about too much in matrices and lists because they're just arrays and linked lists. So the idea of this is just to give you an idea since, okay, 1 second. Okay, right, our first lab is very much this class except in C++. So I can't just take my code and turn it in because it's not in the right language. So if you get stuck, you can refer back to this, but you're going to have a square matrix and we'll talk about the code because especially dynamically allocating a square matrix in C++ really isn't even possible. You have to kind of enforce it yourself. But so here's our matrix. These are the edges that exist in the graph. So when we go ahead and use our constructor, create the graph, we just create our matrix and we're going to have a separate array that represents the labels, right? So labels are alpha, beta, gamma, delta, an array of strings. That's the alpha, beta, gamma, delta. And when we go ahead and add an edge to the graph, we just do a lookup. The comma makes this 2 dimensions. All right, so this is C#. So yeah, syntax a little bit different than C++. I'll grab the Stack Overflow link. I can show you. It's funny. There's several different answers, and you know, I want to make sure I direct you in the right place. All right, so adding an edge, they just say where we're going from and where we're going to, and we just find where we are in our label list, the index. So if it's the first, if it's alpha, right, get the index is 0, and we're going to beta, index is 1, and to set so that the edge exists, we just set it to 1, the edge exists. The way this is coded is allowing us to do multiple edges for between a pair of vertices. So it does a plus plus instead of just setting it to 1. And the way that this is coded is it's doing it in a digraph. If we want this to be a symbol graph, we just come along here and mirror it by mirroring the operation across the diagonal. Now it becomes a symbol graph. Symbol graph style, where it means all edges are bidirectional. All right, and printing out the edges, just nested for loops going down. And if it's not 0, it says an edge exists. And that's pretty much, right, it's just 2-dimensional array. That's really only thing that makes the matrix anything more difficult than what we've done before. The adjacency list, right? A node, single linked list node, it's got the data, it's got the next pointer. Overloaded constructor, nothing really special there. And we have our list class, right? Someone to represent the beginning, someone to represent the label for this particular list. So we're gonna have a list for alpha, list for beta, list for gamma, however many vertices there are. And the add, right? It's just a sorted insert. So create the node, do our check, see where is it. The first one, is it going in front of the head or are we iterating down to where we need to go, right? So same kind of code we've seen before for sorted single linked lists way back February, January. I don't know, we're halfway through the semester, so I'm starting to lose track of how long it's been. And then the print just prints out all the values in that particular list. Then we get to No data. Don't worry about that one. That's just you put the label and weight separately. You just bake that into the node class instead of just doing. I'm using generics here, aka templates. So feel free not to do generics or templates. Just hard code a double and a string for data points as those come around. But finally down to list graph, right? So obviously link-based code involves a lot more code because there's a lot more structures, a lot more pieces in the structure to make that structure happen. But eventually we're getting the actual list graph. Here we have an array of our linked lists. All right, so here's my linked list class and an array of it based off of our node data for a generic pattern. A constructor just to initialize everything up based off of the vertices that exist. Right, create the array to be however big that list of labels is going to be, and then set the labels and then set the individual lists to be empty lists at that point. And add here's a little bit more code, but it's still the same idea. Where we're going from, where we're going to, and this one is also inclusive of weight, where the matrix one was a different style. Iterating through till we find who we're going to, create the node, and we're adding it to the list. This one is not, oh no, yeah. So the sorting is happening over in the list class. So find the list to add it to, and then add it to that list, and then the sorting was happening over in the list class. Well, I didn't have a project open. And a menu, whatever menu. You don't need a menu for the lab. But if you want to, you can download this, open up a C# console application and play with it. If you need help on how to do that, I can show you, but otherwise, right, the lab is based off of, or very similar to this one. So there's not a whole lot of code that's going to be needed. Let's see that. Let me C++ dynamically allocate 2D array. And Geeks for Geeks showing up at number 1 now. Okay. All right, so let me constant. Yeah, no, we don't know the constants all being dynamic. All right, so here is what you need to do to dynamically allocate the array. It's a star star. Star star. So an int star is a single dimensional array, and star star allows for us to have an array of arrays. So it's technically a jagged array, even though we want a rectangular array, really a square array. So each element in A is an int star. So when we new it up as an int star. And then for each of those, we new it up as a new int array. And so this is effectively what you get here. They have a nice picture, right? 0, 0 goes to the first list, and the first element of that list is that first position, right? So if we wanted to go to 1, 1, 2, 2, 3, 3, et cetera, et cetera. They didn't quite do a, this drawing is not quite right. That's not exactly square, but get the idea, right? So the way the memory in this allocated is not like a 2-dimensional array. So if you go and like just allocate on the stack a 2-dimensional array, just like when we did a couple weeks ago, right? That memory allocation, that's all a physically contiguous array, but there isn't actually a syntax in C++, at least that I've ever seen. I've searched a couple of times. I don't know if the newest version has it or not. That allows us to allocate dynamically a 2-dimensional array and actually have it do the column and row indexing for you. You can wrap it yourself by just doing the row times the column and say, okay, I need 40 elements, create an array that's 40 elements, and then do the mapping in the code yourself, but so these are actually physically separate arrays. So it's 4 separate arrays. So they may not actually be contiguous. So it's a double indexing operation where we index to get to the particular array we want, 0, 1, 2, or 3. And then we index again once we're there to get to the particular column in that array. Right, so this one also has a cleanup for you, but lots to answer this one. This question was, I don't know, how long was this question asked? So it's definitely been viewed a number of times, right? Yeah, 13 years ago almost. Yeah, other languages like, well, I was just showing you C#, it handles it a little bit better. And C++ has been around for a long time. And, you know, things we could do back then are limited compared to the things that we can do now. So it's just a little bit more cumbersome, but it's good enough. And if you can't figure out the dynamic allocation, you want to create the array on the stack, whatever, doesn't much matter. Really, this is about the algorithm of figuring out where the vertex is supposed to be and turning it on in the matrix and then showing that it gets turned on correctly. Right, so that's the lab we have. March. We got matrix. This is next week. And we just exercise with matrices first. Right, ask them how big it is, and then ask them for the labels. Right, so you have a two-dimensional array for the matrix, and you have an array for the labels. And then the user just says what those labels are going to be, and then they add edges to the graph. And you can spit it out however you want. It's probably best to actually print it out as the matrix, the zeros and ones. That way you can see that your code is correct, because it's quite possible to produce correct output but have incorrect code. Questions about Matrix Lab due tomorrow? Okay. More graphs then. Try it again. All right, so a path is a sequence of vertices in a graph. Typically, have more than one way to get from vertex 0 to vertex 1 in the graph, and some paths could repeat. Okay, so let's see. Home, office, school, that's pretty good now. Good enough. Office, school. It's another point. Let's see, where's a good place to go to lunch? I saw Jack in the Box, that's too long. Right, in and out. That's nice, short name. Short enough anyways. All right. Okay, so let's say we started the day, right? Started the day at home. Then we went to work. Then we went in and out. Then we went back to work. And then we went to school. And then we went back home. All right, that's it. That's the path that we may have taken on a particular day. Right, we may not have had, say we have a fun Saturday class and went home to school and back home, and we didn't bother stopping for lunch anywhere, right? Different paths that we could take. And some of these paths are repeating. All right, so we went from here to here, to here. We came back, and we went over there, and then back home. All right, so we repeated a vertex in the middle of the path, eventually completing our circuit cycle, getting back to where we started at the beginning of the day. All right, so there are different types of simple paths, and I will just give you some links. Read up on these. A simple path, we got simple cycle, and then we've got circuits and all kinds of fun stuff. I'll clean this up later once I provide the links for you. Just read up on it. That might apply. I guess I should take a screenshot of that. Right, that might exist for the flow of data or actions or whatever may have been going on to get us from here to there, the other place. And some of these paths will adhere to certain characteristics and some will not as we're doing things. So I'll just do this one. This one's mostly a reading exercise. I'll post some reading on that and we'll check it out. Thanks to follow for these paths. Now, some paths get a little bit more involved. Hamiltonian paths. Trees. Tree. Can you make terms confuse your graphs, right? So Hamiltonian graph is a graph that contains a path such that we do not repeat any vertices within the path, except possibly ending where we started. If we end where we started, then the path is a Hamiltonian circuit. If not, that path is a Hamiltonian trail. Okay, so let's get a graph in here. And we'll make some paths. Six points, A through F. And we'll just connect up with a cycle on the outside, then do some crossing over. A couple points in the middle. All right. So what is the following path Hamiltonian? Is it a trail or is it a circuit? So we can create a path A, B, C, D, E, F. For that, a little detail, and every vertex in the graph is used in the path. All right, so we have A to B, B to C, C to D, E to F, D to F, and then E to F. All right, so we did not repeat any vertices. All right, so no vertices. Repeated. So the graph is Hamiltonian. And we can still go from F to A. So it will be a circuit. So let me add that to the path. Hit every vertex and it where we started. Gives us a circuit. Not every path that we might create necessarily be that way. All right, same graph, we go A, F, E, B, D, C, for example. So we go from A to F, to E, to B, to C, to D, but we don't have an edge. That takes us from D back to A. So we've hit every vertex. So we have a Hamiltonian trail. Right, it's the same question as we had before. Screenshot of it. It's interesting how the screenshot is bigger than the actual. Must be a zoom thing going on there. Okay. All right, and let's do the same thing, but then we'll keep going further and identify going to B, then A. So here we have no, not a trail, not a circuit. That path is not Hamiltonian. And the problem being there was a repetition in here. B exists twice. Since it exists twice, we repeated. And since we repeated, that makes us no longer Hamiltonian. Order correct. With our path here going from start to finish. And actually, yeah. Discovering these paths is a little bit tricky. We're not going to go into the algorithm for how to discover it. Usually if we have a visual, it's easy enough to see. Look to see if there's any cycles in the graph, right? We have several cycles. There's all kinds of cycles in here where we can start somewhere. So A, B, E, F, A, right? That's a cycle in the graph, right? If we were just get rid of, right? If we were to get rid of a few pieces of the graph, right? Just have A, B, E, F. right? Just a cycle graph. And so we've got a cycle within the graph itself. Hamiltonian is trying to see if we can get that to be all vertices in there. Basically, effectively trying to find a subgraph within the graph such that we're hitting every vertex exactly once. Right, so shaped graphs and Hamiltonian. Right, so cycle graphs are always going to contain a ham circuit, ham radio, whatever you want to call it. Star graphs, right? There are no cycles, so there will not be a circuit. A small star graph can create a trail. Wheel graph, same as a cycle, always gonna have a Hamiltonian circuit. Right, we just basically travel the outside of the wheel just before we get back to where we start, jump into the center, and then go back to where we started. And since that created a circuit, we could start anywhere in that circuit and get back to where we started following that exact same path. We're just shifting the order of the vertices. A complete graph. Since we can get to anywhere from anywhere, we'll always have a Hamiltonian circuit. Then when we get to complete bipartite, this requires case-by-case analysis for you to dig into on your own. We will find that some have the connectivity that we need to find trails or circuits. Okay. One more topic. Spin into the lab time. Point 3b. Eulerian. I said graphs, right? Yeah, graphs. Go for consistency. So Euler is like Hamiltonian graphs, except instead of creating a path hitting every vertex, we want to consume every edge. And easy way to remember the two of these. Euler spells his name with an E, and he cares about edges. Take my keyboard apart this week and try to clean it out. All right. This is actually probably a game that you've played before. There's a game that asks you to draw a house without lifting up your writing implement. The house has 4 corners and a roof. And across the middle. So let's draw our house. right? So the game asks you to draw, right? Start drawing the house somewhere and try to draw it such that you use every single edge in the graph and make your house. But I did not manage, right? If I redraw over here, paths that I took, I failed to draw my house because I got stuck here and I can't reuse an edge. It's not allowed. So finding the solution to this is actually, let's see, can I just make all of everything bigger? Does that work? That works, perfect. Is easy. Euler is easy to figure out. All we need to do, let's get my numbers correct in here, is look at the degree of every vertex. All right, so remember the degree is the number of edges that connect to the vertex. So this top vertex has 2 edges incident with it. Here we have 4. Here we have 4. And then these 2, we have 3. Vertices that have an even degree means that for every road in, there's a road out. Right, so for every road in, there's a road out, in and out type thing, right? So this 4 has 2 outbound, 2 inbound. So when we create a path, it comes in and then goes back out, it goes from 4 to 2 edges still unused on that vertex. So the key to solving Euler is we need to start at one of these odd degree vertices because we're going to start there, and as soon as we start there, we're only going to be leaving 2, right? We're leaving 2 edges that we can consume later, giving us one way to come in and one way to come back out later. So by starting at the odd, we can find a path, and there are several answers to the solution for what the path needs to be, such that we can do this without lifting up our pen and hit every single edge exactly 1 time. So we will be starting at one of the odd degree vertices, and we will be ending at the other odd degree vertex. So identifying if it has one or not is trivial. All I have to do is the numerical analysis. Look at the matrix or the list and see the length. Okay, so we're doing the lists. So look at the length of every list. If it's even, don't bother counting it. If it's odd, increment a count. And at the end of counting the lengths of each list, if we have more than 2 that are odd, then it's not Eulerian. If there are only 2 that are odd, then there's a trail. If there are none that are odd, then it's a circuit. So recapping what I just said, determining graph has a trail or circuit where neither, that is Eulerian. We look at the degree of every vertex. If they are all even, then there exists a circuit. If all are even, save for 2, then there is a trail. Otherwise, neither exists. It exists. Right, so cyclograph. Right, cyclograph. Everyone has a degree of 2, right? So that's all even, so we're good to go. A star graph. Right, everyone has a degree of 1 on the outside, so only for very small stars, right? S3, we have 1 even and 2 odds. S2 is 2 odds, and S1 is, right, we can make a trail. And only trail, wheel graph. Okay, for their wheel graph, the degree of everyone on the perimeter is 3. So that's going to be a lot of odds. So no luck here with all of the 3 degree vertices, and assuming we're at least 4 vertices for it to actually look like a wheel. I'm sure some authors will try smaller definitions, but it's just, yeah, that's mathematical in nature, not really graph theory in nature. Complete. This one's going to depend on the number of vertices, right? If the number of vertices is odd, then the degree of every vertex is even. So we'll have a circuit. Complete bipartite for you to dig into. We'll find that some we'll have trail or indoor circuit paths. And so it's all about even oddness of the vertices. So just identify what circumstances would cause the vertices to have even degree or not even degrees. Not even degree, we have that cap of 2. If it is even degree, then everyone has to be even. This kind of makes sense. Let me dig up. This one's been around. Bridges. Here for a long time. 1700s? I can never remember. When was this? When? Do. All right, yeah. Yeah, 1735. So a lot of graph theory has been around for very, very, very long time. So I'll let you read on this. Basically, people are trying to figure out if they could get across all these bridges without having to reuse any of the bridges. So Euler went ahead and developed some math for it. And now it's part of graph theory. Yeah, you read up on this good stuff. It talks about what you can do there. Right. Check out the C alsos. A lot of this graph stuff is cool. An actual like laying things out. Actually, I assumed one time where he worked for a construction company, and when they're building an entire development, when you're building an entire development, you have to put in sewer, water, electrical, gas. There's all sorts of utilities that need to go into that development. So you're going to have a main trunk that's going to come in and develop somewhere, and then that trunk needs to extend out and connect all the houses, right? And you're not going to have like a complete graph, or a star graph rather. Right? You're going to have a star where every house has a pipe going directly to that trunk line, right? Because that would be a lot of pipe to lay. So you're going to find it's going to have some sort of tree structure more likely. They might have some circuits in there for some redundancy in case they need to do like a bypass. We need to go in and shut down the gas at some point. So there might be like substations type thing in there so it's probably going to be largely tree based, but they might add some circuits so that in case a line needs to be replaced, we can still keep service up to as much of the people as possible. But sometimes service has to go down for maintenance, and that's just how systems work. So a lot of things that we're looking at here in graphs, that's areas of application we'll find are going to be, a lot of them are going to be physical space. And we'll see some of that when we do, like minimum spanning trees would be a key example for that. Otherwise, I need to dig up some links for you for this one. Side. Otherwise, any questions about the Matrix Lab? There's no additional lecture for tonight. We're done with the lecture. We can go ahead and hit the code. Some of you have already done it. It's good. As usual, if you get stuck on the code, start tossing it in Discord and help get unstuck.
Are you going to be posting like the C# one on the files section?
Yeah, that's in the file section.
Okay, cool.
It's in files, graphs. It's the only file in there.
Okay, thank you.
Yeah, so that'll help you with the structure. It's not going to help you with the syntax. Okay. All right. Next test. Okay, we'll look at the syllabus. Next test. We're getting no class next week. Test 3, just on trees, or we have to practice the next time we meet. I will make that available the next few days, hopefully later than Friday. So you can work in that between now and next time. You got program 3 also in that window. Yeah, we'll get to our tree tests in 2 times from now. So go over the practice test next time and take the test 3 the time after that. Yes, test 3 is just graphs. Remember, just in general, the first section in the note, the numbering system, that's where we're being tested on it. Section 3, which is all trees, all trees. Test 4 is going to be all graphs. Right, and of course, trees are technically graphs, but yeah, no other types of graphs other than trees. Because things inherently bleed with data structures. Yep. All right. Anything else? All right. Have a good night. We'll see you in 2 weeks on video, audio, and on Discord in between now and then. Have a good break if you're actually going somewhere. The world's kind of opening up. It's crazy. We're getting back to normal. Normal feels crazy, relatively.